Okay, good afternoon, everyone. Welcome to this revision session. So during the week, I requested that you send through questions, and I do have some questions from Mohammed there. So I've got your document, and we'll just open it up and we can work through that. But maybe before we get into solving the problems, just to ask first, if anyone would like to revise any aspects of the theory and the material. And then any questions or comments and things like that. So I will be sending out more specifics about the upcoming test and the length and so on. I guess I would just follow the same format as you had for your first test. So that would be next week, I think it's next week Friday in the same slot, right? Well, not the slot, but the 2 p.m. slot. Okay, so I hope the semester has quieted down a bit. I know things were quite busy with assignments and so on, and that now you've had a chance to work through the material in more detail, and you have a bit more of an understanding of the course. So anyway, let's have a look at the questions. And I'm just going to share screen here. Okay, so here you'll see that there is that set of notes here, number 7, which we omitted to include under your folder, but that is material we covered in the lectures and so on. So just now you have the PDF for that also. So looking at our questions, let's go to the questions that Mohammed has sent to us. And Mohammed, maybe you can speak up and just let me know if I'm interpreting your question about this properly. But you were asking about in tutorial 4, question 1. Here, you are given a process. Well, you're given the graph of a process, and we are interested in implementing control here. So it says PI control. And we can see in the graphs that, let's see, we wish to implement, and it says here, the diagrams of the Nyquist and Bode diagrams of the process are given below. So when it says it's of the process, that means that's without the PI control implemented as yet, right? So these are the process diagrams. And then the question you wanted to have a look at was calculate the gain and phase margins without PI control. So that basically means look at the system as it's drawn here, right? So as we said, this is about the process without PI control. So the question is basically asking us, tell me about the gain and phase margin just by looking at these diagrams. So is that the question? Yeah, maybe Mohammed. So we can go through that and just see how to get the gain and phase margin. Is that what you wanted me to cover there, Mohammed? Where are you?
Yes, Prof. Thank you.
Okay, sure. Okay, so in fact, before we look at this exact question, let's have a look at calculating gain and phase margin in general. So you'll find in the notes here that this is the concept, right? It's all about looking at how close we are to this -1, 0 point, right? So we know that if we encircle -1, 0, then it means we have an unstable system, right? If we encircle -1, 0, that means we have a pole in the right-hand plane, and that means the system will be unstable. So gain and phase margin is all about trying to figure out how close we come to this critical point -1, 0. And you would correctly say, well, I can see that here already, right? This is my Nyquist plot. I can just look and tell you, I'm not encircling -1, 0. And the closest I come to it is maybe around here. Maybe this is about the closest point I come to it. So number one, you could say, well, if I have a Nyquist plot, I can just tell you that. And so the question is, well, then why do we need this concept of gain and phase margin? And that's because when we do the frequency domain dynamics, right, when we apply sine waves at the input and we collect the magnitude ratio and the angle and so on, then we that lends itself to drawing Bode diagrams straight away, right? Your frequency domain plot, yeah, you can use it to draw this curve, but typically it's more usually the case that you'll go ahead and draw the L and theta versus log omega graphs instead, right? So number one, you can just go ahead and say, well, on my Nyquist diagram, I can easily see how close I come to -1,0, because that's what it's all about. That's all we are trying to determine here. The whole concept, gain margin, right? What's the margin before I start getting closer to the -1,0 point? And in fact, let's draw a little bit here. So if this is, if these are our axes, and we are worried about this -1,0 point and encircling it, right? Let's say that's the point. And then let's say this is our process, or maybe it's the process plus the controller. So for our current control settings, maybe the process is looking like this. And then as we increase Kp, then the process might start doing this. And then if we increase it a bit further, then it might start to just touch on this point here. So we would like to know, for example, when is the Kp value becoming too large, right? So let's say we said as we increase Kp, then we get these different curves here. So you can see here, when for the Kp value, like, maybe this is a Kp of 1, maybe this is 20, maybe this is 50. So we would say, okay, when Kp gets to about 50, then we are starting to become unstable. So we can see we never want to go to a Kp value beyond 50. And then we also don't want to stay on 50. We don't want to be operating right near the point of instability, right? We don't want a controller that's nearly making our process unstable. So what we would like to do instead is leave a nice margin, right? So we would like to say, okay, I want to stay this far away from the -1,0 point. And that would tell you, maybe I can only use a Kp value of 2, right? So maybe Kp equals 2 will get you there. So you see, if you can set your margin, the margin that you are staying away from -1,0, if you can set that margin, then that will help you decide what the controller is. And towards doing that, you first of all have to be able to look at the process itself and saying, okay, before I even implement control, right, when Kp equals 1 and tau I is infinity, how close am I getting to -1,0? Right, so that's then the concept of the margin. And we can define this margin in two different ways, because in a sense, we can see here that it's not enough to look at just one point, right? So we can draw just the distance here on this axis. But what if we have some weird graph, maybe something that looks like this, right? If your process had this weird shape where it looks like a nice margin here when you look at just the intersection, but then you find that actually the closest it gets to -1,0 is this distance. So we use two margins. We use the concept of a phase margin and a gain margin. So this is the phase margin shown here. So for the phase margin, we say there's my worrisome point, this -1,0. And so what I want to do then is produce the unit circle here. And I just need to move okay. So you can see here, here's the circle that tells you when you are close to being -1. So you produce this -1 circle because we know it's going through the -1,0 point. And then you take your curve and then you look at where this curve crosses the -1 circle. So right, the solid line is your process. and you look at where the process comes close to this unit circle. And then you take the angle between your negative real axis and that point of intersection. So would you agree this is a good measure of how close you come to being like -1, right? And I say like -1 because it's not exactly -1, it's shifted by some angle, but it's the angle that gets your process the closest to having a magnitude of 1, right? You agree with that? This angle shown here is a measure of the angular distance between your process and being -1. Okay, so that's the concept of the angle. How far away in terms of the angle are we away from -1, 0, right? So to get that, we look at when is the magnitude of the process equal to 1, right? So that's the concept of your phase margin. And you can determine this also from your Bode diagrams in this way. And you'll see it's a bit more complicated, right? On the Nyquist diagram, it's very nice and easy to see what it means, and we can draw a nice picture like this. On your Bode diagram, you have to think about it a little bit more. So you see, number one, we can say all points along the circle are where the process has a magnitude, where the transfer function of the process has a magnitude of 1, right? And if the magnitude is 1, we know that the log modulus is 0, right? It's log base 10 of 1, which we know is 0. So the first thing we can do is on our Bode diagram, we can look for the L curve. So here's the L curve. And now we know it has to have an L value of 0. So we can produce the 0 across and say, okay, that's where L equals 0, right? Because then we can say, yes, that is where L equals 0. And now we can produce that down and say, then that is the log omega value. So that's the frequency at which the process has that value of 0, right? So that's the omega. And then we say, well, then I can go over to my theta graph and I can look up the angle. So here's the theta graph. So I know normally we draw them separately. Normally we draw a subplot for L and another subplot for theta. But we've drawn them together on this one set of axes here, and you've got L values on this side of the axes and theta values here. So we've chosen L equals 0. We've produced that down. That tells us what omega is. Then we can use that omega to go up to the theta curve and say, well, then that is my angle. So we can look across here. That's the angle. And then you can look at the difference between the angle where it intersects and 180 degrees here, right? So you can see it's still inside of that angle. In other words, when L equals 0, we haven't gone past 180 degrees. So we can say we have not encircled -1, 0. And furthermore, this is the phase margin. So in terms of the angle margin, this is the difference, right? That's my actual angle. And then that -180, that tells me my margin there. And as I say, you can see it conceptually much better over here. Any questions or comments on that? So Mohammed, does that cover the concept? We'll come to the actual question just now, but does that cover the concept there? Okay, and now let's look at the magnitude, right? So that is so we've talked about the Nyquist flux and the Bode diagrams, and then in terms of your Nichols plot, yeah, your phase margin, as we said, when L equals 0, remember your Nichols is L just plotted against theta, right? Bode is L and theta plotted against omega, and your Nyquist is just the is just the complex number for G. So now for the Nichols plot, it's L against theta. And so again, we can choose where L equals 0. So that's where L equals 0. And then that tells us straight away, that tells us what the angle is. And then we want to know how far that angle is from -180, right? So this is all about the phase margin. Now let's go over to the gain margin. So the gain margin is now saying, let's consider the angle. Let's fix the angle and look how far we, or look how close we get to -1,0 with respect to the angle. Right up here, we were saying, let's fix the distance. So here we fix the distance at 1. And now the other thing we can do is say, well, let's fix the angle. Instead of saying we can be anywhere on the circle, now let's say we could be anywhere along this line, right? This because it's all about how close do we come to -1,0. So in terms of moving along this line, we then just look at where does the process intersect with the negative real axis, right? Because the negative real axis is also where -1,0 is going to fit. So we define the gain margin to be 1 over the distance from the origin to where the process intersects with the negative real axis. So again, on this Nyquist plot, it's very clear. You can see your gain margin is a very clear indication about how close you come to -1,0. And then to figure it out on the Bode diagram, you would go, so we said it's the negative real axis. So that means the angle here is -180 degrees or +180 degrees, right? And typically when we draw the Bode diagrams, we work quite consistently. We try to keep theta to be negative. So between 0 and -180 degrees or 0 and -360 degrees. So we are counting this as -180 degrees. So we would look on the Bode diagram, we look for -180 degrees and we look at our theta curve. So it intersects here. So that means that's the omega value of interest. And then we can produce for that omega value up, and then that tells you what L value we have. And then if we look at this L value, this is a negative L value. That means it's a fraction of 1. So we are still inside, we are still not encircling -1,0. So that tells us the distance, sorry, I was pointing here. This is actually the 0 for theta. I should be pointing here. This is the 0 for L, right? Because we're plotting the two different curves on the same axis. So here's L, there's the 0 for L. So we know that the actual L value, where the angle is -180 degrees, is this value. And so the distance between this value and our 0 here, that's an indication about our gain margin, right? So that's the distance for the gain margin there. And then you can do the similar thing for the Nichols plot. You can look for -180 on the angle and then produce that up. That gives you the corresponding L value. And then you look at the distance from 0 there. So again, it's all about how close are we coming to -1,0. And so if we have a look at for the problem that's given here. So we want to know the gain and phase margin without PI control. So that means just go ahead and look at the process graphs here. So if you want the gain margin, that means set your angle to -180 degrees. And here I've kindly provided the -180 degree line. And you can see here, this graph is, it's got an L value, which is a tiny fraction, right? When you see a negative value like this, that means the actual magnitude of the gain margin is a very small number. So this is very close to 0. This is 10 to the power -150. So that's approximately 0. So you can say that that must be this point here, right? Because -180 degrees, we can see that's the negative real axis. So we are probably looking at a point very close to the origin here. And then when we consider the other intersection, so the other -180 degree point, so that's here. So when we look up this point, right, so you can see it's just to the left of this line. And so just to the left of this line, it's still negative. So the two intersections you have are fractions of 1, right? If your first intersection was less than 1 and the second intersection was more than 1, then you would say, well, guaranteed, then I have encircled -1,0 and I'm not stable. But now you can see definitely it is stable. Both the points are staying away from -1,0, so we're still here. Now, That's all fine. You can comment on stability like that, but the question is asking you about the gain margin. So in terms of the gain margin, you actually have two options here. You can say the distance between this red point and the blue point, or the distance between the red point and the point of intersection here. And the one you would choose is, of course, the point of intersection, because the whole concept is you want to know how close you ever get to -1, 0. And so the closest you get is this point here, right? So this would be the gain margin that you use. So you would take this distance and say 1 divided by this distance, and then that would be your gain margin, right? And then the other side of it is the phase margin. So we would ask, when does this get close to the unit circle? So you would look here and you can see the 0 is here. So you produce this down. You can see it's going to be just to the right of this line. So coming down here, just to the right, yeah, coming down here, just to the point of intersection is just to the right of this line. So that's here, it's somewhere here, right? So this is less than -180 degrees. So that means when your magnitude is equal to a 1, you've gone past 180 degrees. So by the time this thing gets to a magnitude of 1, which is probably around here, then that angle is already gone past -180 degrees. So that means we haven't been able to encircle that point. And so you could use those two facts together to say, no, I'm not unstable. And secondly, you can just report that that's how far away from instability I am. And of course, you can see here, you can imagine lots of situations where this is not going to work so well, because you are relying on just these two metrics, right? Gain margin and phase margin. Whereas what you should be doing is looking at this Nyquist diagram and saying, look, the closest I get is actually a point here, right? If you think about it, you can imagine a circle wrapping around this red point. And so the closest you get to that circle is actually a point here. That's really an indication of your margin away from instability. But anyway, these definitions were proposed kind of for historical reasons, because it was much easier to work with a Bode diagram and to just go ahead and get those two measures. It's also much easier to code up this kind of thing. But that's what it means. It's all about closeness to -1, 0. Does that answer that part of the question, Mohammed? Okay, let's take that as Mohammed's. Okay, you were about to reply there?
Yes, Prof. It answers the question. Thank you.
Okay, thanks. So that was the first one you put forward. And then in the second problem, we asked, let's see here. Okay, so this one, it seems you didn't have a question on this one, but here you are asking us to go over these questions. So here, find suitable values for KP for proportional control. I'm not sure why you crossed this out. So and you've been seeing across all the tutorials, I've been repeatedly giving you these same transfer functions, right? And I have a nice tool for you to play around with the equations. So it is in your tutorial folder. So if you look in the Dropbox folder, you can load up this controller design Python notebook, okay? And I'll just show you what that does. And I am going to also show how you do it without this, but I just want to show this because we can, let's look at some of the graphs first. Just trying to find my phone. Here, okay. Right, so I wrote some code that would help us draw all those graphs for any given function. So you'll find here, there's some code written for generate frequency domain dynamics plots. And so here it generates a series of omega values. So you specify a list of omega values here. and then it will create your S values. Now remember, it must be S equals I omega. So we are generating complex numbers with a 0 real part and omega as the imaginary part. So this is saying S equals I omega. That's what this code means, right? And then we just go ahead and apply all those, we go and apply all those S equals I omega values in here. And that will generate for us a set of G values, our process values. So whatever we've defined our process function to be, we'll get a set of G values here. And then, of course, we can extract the real parts and imaginary parts. So you see in Python, you've got, let's just, so in Python, you have a nice set of functions that make it very easy for you to extract the real and imaginary parts. And then you can take the square root of the sum of the squares of the components. But there's also in the NumPy library, if you just say abs for absolute, so in other words, the magnitude of this real number, then that will give you the magnitude. And then, of course, the angle, so arctan of the imaginary part over the real part. And if you use arctan 2, then that pays a bit more attention to which way you've written it gets the quadrant right? If you just go arctan, then, because of periodicity, you don't get quite the right angle, but this does look at each one in turn, right? Arctan is just a single argument, imaginary divided by real. If you use arctan 2, it looks at the components of those and gives you the angle correctly. So that's really all the information we need to plot the Nyquist diagram and the Bode diagram. And then you'll see also that the Nichols chart, right, is also calculated here. So those curved lines, so if you follow the lectures, you'll see that the closed loop diagram, that's also shown here. So here I'm not using a chart, I'm actually generating these lines on the fly. So all these curved lines, they are generated from the equations also. So all this code does all the work for you, and all you need to do here then is specify the process transfer function. So you can work through all that code, and here are a bunch of the equations of interest. So let's look in Mohammed's sheet here. Let's see, did I put this one in? Yeah, looks like. So let's let our process transfer function be this 1 over s plus 1 times 3s plus 2. Yeah, so that's that equation. And let's just use this tool to plot it out for us. So let's run this. Okay, let's run. And by the way, I use this little blue cross to help me figure out where on this curve I'm starting and where I'm ending. And now you'll see this curve, it's not really complete as yet because we haven't gone far enough with our omega. So let's just jack up our omega to 2.5. So this is 10 to the power minus 1.5, 10 to the power 2.5. So we are going from 0.1, a number close to 0.1 to something over 100 using 100,000 points. So it's quite a smooth curve. So if you run that, so now you can see it's wrapping there. And if you look at the scale here, -1, 0, there's the red point. So we are not coming close to that. So clearly this process is stable. And let's now look at the Bode diagram. So you can see the Bode diagram shows that in fact this the magnitude of G never goes above 0. So it's always less than the unit circle. So where's 0? 0 is here. So throughout all the values we considered, it never went above 1. So our log modulus never went above 0. So it's always stable, right, in terms of this process. So that's L. And then we can also plot our theta. And so theta looks like this. And then, as I say, we'll go just now to looking at how do we draw this without code. But let's just keep looking at this and understanding what it means. So you can see here, we are starting with the asymptote at 0. It goes through its transition, and then it ends up at minus 180 degrees. So you would normally look here for your gain margin. Where's 180, and then where is that? And you can see when you reach minus 180, your magnitude is so small, right? And you can see that here. When you reach the 180, your magnitude is so small, you're staying far away from minus 10. So you've got those two, and then you would use those two graphs to find L and theta values. So you construct the set of values here. So your starting point, which is here, you would take this value and this value, and you can say, right, actually it's here then, right? So your L value is small and your theta value is small, meaning close to 0. So you start here, and then as you choose different omega values, then you get different L and theta values, and then you get this green curve. Now that's messing up our scale here. So let's just drop the frequency range a bit. Let's just set this back to, let's try 0. And okay, so that's better. And so we can see that our closed loop line, we know that the desirable operating line is this one, right? LC equals minus 2. So LC equals, so this line we know is a desirable operating line. So we would like to shift this curve such that it becomes a tangent there. And what's nice is, or for the proportional controller, what makes it very easy is that the proportional action only contributes a vertical move, right? So because proportional control will never have an imaginary part, right? If you look at the equation for proportional control, it doesn't have an S term in it. So the fact that S equals I omega doesn't affect the proportional controller. The proportional controller just stays on KP. So as you increase KP, you only shift this, this entire green curve only shifts vertically. So you can look at, I think this green curve could be a tangent around here. So you could look at what's the distance between this point, right, which is close to 0, and this point, which is, say, minus 12. So you could say, looks like I need to use a plus 12 shift. So if the green curve shifts up by 12, then you'll be tangent to the LC equals minus 2 line, which is a desirable place to be. Or sorry, LC equals 2, not minus 2. So you would shift until you are tangent here. So let's say that's a 20. So you've shifted by 20, and a shift by 20 in delta L means your KP is 10 to the power 20. So let's look at that. Let's see if we can actually put that in. And we do that by, right, remember the proportional control, it just multiplies the whole function. So let's try a value of 10 here and see what that does. So if you apply a 10, you can see now that we are getting closer to this value of 2 here. We are still stable, right? And in fact, we should use more values for omega, but we can see by the time it gets here, it's moving away again. So we are not encircling minus 10. So let's try a bigger value. Let's try 20. Still not encircling minus 10. And now we've exceeded the 2 line. Let's try a 15. Still a bit high. So let's drop that a little, 12. And let's just call that done, right? You can get this arbitrarily close to this line. So the point is, you've now trained your value of KP. You can say your controller works really well for a KP of 12. So that's how you can use the closed loop function. You can say, obviously, I want to stay away from minus 10, But the further away I stay from this point, the slower my control is going to be. So you can create a very conservative controller, which hardly does anything, right? It's so slow to act that it's very stable. But you don't want such a slow controller. You want a nice balance between fast performance and stability. So that's why we choose this value of 2. So in practice, and in fact, not just in practice, if you go back and look at the open loop transfer functions, you look at those 45-degree lines, that will help you understand why this value of 2 is important. So it's known that a value of 2 is useful. It gives us a nice performance. So it's still stable, right? It's not going into that -1,0 point, but at the same time, it's not so slow that the process takes forever to respond. So, so we try and shift our green curve, which is obtained by producing all the Bode diagrams. We shift that green curve until it's a tangent approximately to this LC equals 2 line. And then that tells us what the KP value was. Does that answer it so far, Mohammed? Okay, Mohammed is just warming his mic up there. Okay, so that's what you can do in this case. And we can look at, as I said, this is all in code, but let's look just now at how to do that using pen and paper only. So anyway, that was the first one you asked about. And then you also asked about this function. So you, well, all these, but let's look at this one. Okay, let's look at both these. So let's run this one. So running that. So this one does wrap around here, but it never wraps around -1,0. And you are already tangent, nice and tangent to LC. So this one, but I think I was playing around this, and so you see that value of 5 there. That's the controller, that's your KP value. So that's so using a controller of 5, a KP value or KC value of 5 gets you good performance because you are tangent to this point. And let's see what the other one looks like. So you've also asked about the one where you've got that third term in the numerator. So you have this term up top. How does this look? Right, and here you can see it's going to be quite hard to get this close to the 2 line. So proportional control alone won't do it. You have to use integral control, which will also shift you around horizontally. Okay, so so that's how you can, and you can play around with this, stick in whatever transfer function you like, and get an understanding of how the control curves look. So let's step away from the code now, and let's look at how we would do this if we had to just use pen and paper. And the other side of it is, besides looking at a nice, easy KP or a proportional control, what if we had integral control? What if we had derivative control? How do we handle those cases? So let's pick an example here. I want to take something which has enough of a challenge, but it's not going to take us forever just to talk through it. Yeah, I think let's just go with this one. Right, so s plus 1, 3s plus 2. So GP equals 1 over s plus 1, 3s plus 2. So what we want to do is get our log modulus. Let's think about that. We could also just look at let's just first apply I omega and see what that looks like as a real number. So if we apply GP of I omega instead of just a general S. So I omega. This is, of course, I omega. Right, then, yeah, well, I'm just thinking doing it this way is going to take, well, let's just do the first term first. So we can do here 1 minus I omega divided by 1 minus I omega, right? So we are just multiplying by 1 basically. And so in the denominator, it's going to be 1 plus omega squared. Yeah, 1 plus omega squared. So this is simply, we can write this as, we can bring the 1 minus I omega up here. And here, this is going to be omega squared plus 1. Right. And we can get rid of this. So we've gotten rid of an I in the denominator, in this part of the denominator. Then we have to repeat the same trick for the other part of the denominator. So we multiply by the complex conjugate of that denominator, right? So it's going to be 2 minus 3I omega. So 2 minus 3I omega. 2 minus 3I omega. Which looks like, and so obviously here we can just multiply these two together. 2 minus 3I omega. And then down here, it's going to be 4 plus 9 omega squared. Okay, and then you can just write this as, so we can multiply the numerator. And so here you've got 1 times 2, which is obviously 2. And then you are going to get 1 times minus 3I omega, and then minus 2 times I omega. So this is going to work out to minus 5I omega. And then you are also going to get minus I omega times minus 3I omega. So this is minus 3I squared, which is a plus 3, and then omega squared, right? And then we can say, well, this is a real number, right? If omega is real, then that's omega squared is a real number. So there's my real part, and there's my imaginary part. My imaginary part. Then my denominator is real. So this is, if you wanted to plot the Nyquist diagram by varying omega, you can see now you've got a clear real part. And in fact, we can go ahead and expand this further if you want. So we can write it like this. It's wasting time now. Right. So you've got the real part here. So as you generate different value, so you can run a loop on omega. So you can just stick in different numbers for omega that gives you different real values, and then you can stick in different values for omega here that gives you different values for the imaginary part, and so you can sketch out your Nyquist diagram for g of I omega. So that's one graph you can produce quite easily. Then for the Bode diagrams, we do things a bit differently. So you can say L equals 20 log 10 of G of I omega. And now we've done the work of separating them into these two parts, but normally, okay, let's just use it like that. So L equals that. Oops. So it's 20 log 10 G of I omega. And sorry, this is incorrect. It should be the magnitude of G of I omega. So the magnitude of G of I omega, you can see here. Maybe let's do that separately here. So it's a magnitude of G of I omega equals the square root of the real part plus the imaginary part squared, right? So square root of the real part, which is all this stuff, squared plus needs to be in here, plus this thing all squared, right? And of course, the denominators are the same. Yeah, in fact, I should have just stuck with this here. It's going to be much easier to work with this one. Oh, jeez. So all this squared. So it's going to be this part squared, and then it's I squared, and then times -1. So I squared is -1 times minus here. So that's a plus 5 omega squared. Right, so that's what we have for G of I omega for the magnitude there. You could do some cancellations here if you factorize this, right? But let's say it was some complex function or maybe a complicated function. This is a complex function, but let's say it was also a complicated function, and and so we wanted to graph it as is. So just for a bit of practice, let's say we wanted to go and graph something like this. Right, so we would say, well, we've got a big square root here, so all we need to do is rewrite this as a half of that lot. So we would make this 10 times the log of this thing here without the square root now. So we've used the fact that it's this thing raised to the power half, taken it using the product rule. So there's that. And then we want to separate this further now. And so we can't do anything about this thing in the numerator unless we go and factorize it. So we keep that as one factor, and then we can separate the numerator and denominator. Like so. So take the numerator out here. And then you say minus 10 log 10, and then the denominator here. So we are using the fact that this is this stuff raised to the power -1. So we just took the -1 in front here, and now it looks like that. And then you can't separate this one, but you can separate these two. So we can rewrite this like so. So you would say minus 10 log 10. And you would say, yeah, minus 10 log 10 of this stuff. Right, so you've got these three terms, and now you can go ahead and try and plot this. So you can then use that approach of of plotting each line individually. So like I say, we've chosen to go about this quite a complicated way, but you can do this much more efficiently by factorizing the terms instead. So instead of trying to produce all the stuff as we've done here, you can instead work with the factorized version here. And so in fact, let's look at what we did in the tutorial. Here. That's the wrong one. 2021. So here, for instance, when we had the function, yeah, we separated it. Let's see, this doesn't really show what I'm trying to say. So like here, yeah. So you can, if you have your function in this form, right, 1 plus factor times omega squared, then you can talk about the asymptotes here. So you would say, well, when omega is a very small number, then L, then this thing here is approximately 1, right? If omega is small, if it's close to 0, then this term is small in comparison with 1. So this is log of 1. So in this case, where were we? So in this case, when omega is small, you can see this part is going to be very close to 0. And then it's basically log of 2, log 10, 2. So that's not 0, but it's some finite number. So it's a small number, maybe 0.2 or 0.1, something like that. And then similarly here, when it's when omega is small, then it's log of 1 again. That is a 0. And here it's going to be log of 4. So you can get for small omega values, and then you consider at what value of omega it crosses over. So here, when omega crosses over the 1, then it's going to have the asymptotes. So 0 and then a roll-off of minus 10. And then here, it's going to be a crossover of 9 over 4. So where omega is close to, 4 over 9, not 9 over 4, 4 over 9, then it's going to cross over from that log of 4 over to log 10 of omega squared. And then in this case, you have to solve this to figure out at what omega value it's going to cross over. So what you would do is, let's take this term. So omega squared plus 1 minus 10 omega squared plus 1. So you would say for low values of omega, clearly this is simply minus 10 log 10 of omega, of 1, which is a 0. And then for high omega, you can see that this is going to be approximately minus 10 log 10 of omega squared, right? So let's say this is approximately minus 10 log 10 omega squared. And we can rewrite that as minus 20 log 10 omega. Right, so if we were to graph this, we would say for L, in fact, it's better to move this line up here because the 0 is there. So for L, for values less than the 0, sorry, less than 1, say that low and high, we said, but we shouldn't say low and high. What we actually need to say is for values of omega, which are much less than 1. So for omega less than 1, and this one is for omega much more than 1. So 1 is where the asymptote lies. Yeah, omega. And it's really the log of omega. But anyway, so it's close to 0 here, and then then if you look at it here, it's minus 20 times log 10 of omega. So we are plotting here. We are not plotting against omega directly. It's against the log 10 of omega. And so it's going to have a slope of minus 20 decibels per decade, as they say, as they call that, minus 20 dB per decade. And we say it that way because when we're looking at a log 10 omega plot, then these are, when you see 1, 2, and all that, if you've got 1, 2, 3, then this actually means 10 to the power 1, so 10 to the power 2, which is 100, 10 to the power 3, which is 1000. So for each unit here, it's a factor of 10. So that's where the per decade comes from. Per 10 in omega, it's a slope of minus 20. So L here, this now is also, remember this is minus 20 log 10. So we call that decibel. So minus 20 log 10. So that's where that term comes from. So that's how you can plot that one part of the equation, so that part, and then you repeat like that for this. Here, there's a bit more work. There's that extra crossover point, but you basically solve for the 0. You can solve that quadratic for the 0 and plot that line. So that's how you can plot the L part. And then for the theta, let's just do it here. So the angle G of I omega, so that's equal to the arctan of the real part divided by the imaginary part. I should point here. So the imaginary part divided by the real part. Now here, it's going to be the imaginary part and the real part have the same denominator here. So that's just going to cancel. So we can just write this as 5 omega or minus 5 omega divided by 2 plus omega squared. Omega squared. Right? And if you look at this function, for low values of omega, right, it's going to be 0 up here, and it's going to be 2 in the denominator. So for low values of omega, this is the arctan of 0. So we can say here, omega much less than 1 implies that the angle, and let's just write this as theta, right? So theta equals this thing. So we can say theta is approximately 0. And then for omega, is much more than 1, that implies that. And if we think about that, when omega is very large here, you can see this omega squared is much more than the 2. So don't just bash it in and say, okay, it's infinity divided by infinity. You have to look at the limits here. So when omega is large, then this term is much bigger than this term. So this is approximately 5 omega divided by omega squared, which is equal to 5 over omega. And here, as omega goes for large values of omega, then that's going to go to 0. So that will equal 0. I'm not sure if there's something wrong here. So when omega is large, then that goes to infinity in the denominator. So it's 5 over infinity, which is also 0. Let's just see what that looks like. I wonder if that angle goes down and comes up again. That's possible. Yeah, what function is for this? Yeah.
Is the theta supposed to be arctan of real over imaginary?
No, it's imaginary over real. So that's imaginary and that's real. So I think it's the right way around here. Yeah, that's a bit odd. So I'll have to just check this one. What does this graph look like? When we plotted it, did we see something like that? Which function did we use? So not this one, is it this one? So s plus 1, 3s plus 2, s plus 1, 3s plus 2. So let's just see what our Bode. So yeah, we don't see that here. Yeah, let's just extend this omega range. Omega. Let's make that a 2 and see. Now the angle doesn't go back. So there's some kind of error somewhere here. So it's the arctan of the imaginary part over the real part. I mean, it also does depend from which angle you approach the 0. You know, when you say it's arctan of 0, you know, 90 is infinity. Which one is infinity? Yeah, the arctan of 90 degrees is infinity, but the arctan of 0, it can be 0 or 180 degrees. So I'm not sure if that's the reason that it's always that switched over.
Okay.
Yeah, you get what I mean there.
The third equation when you rationalize 2 minus aiw and multiplied it by 1 minus rw.
So when you say the third equation, just tell me when I'm highlighting correctly.
The third, yeah, this one here in the numerator. Yeah. Is that supposed to be 2 plus omega squared, or is it supposed to be 2 minus 3 omega squared?
So you've got the 2 here, then you've got the I part is going to be minus 2i omega, and then that 1 times that is also minus 3i omega. So that's where you get the minus 5 omega. And then when you multiply this part here, it's going to be 3 omega squared, and then times the minus, so I squared omega squared times 3. Okay, so there's a 3 missing here. Is that what you're saying?
Yeah. Is it not also supposed to be a minus 3?
No, because oh well, I think that's true. Yeah, so there's a minus here. So minus times minus is a plus, and then I squared is a minus. So this should be minus. Yeah, thanks for that. I don't think it actually solves our problem, but yeah, so this is an important correction here. Yeah, but I think what is happening here is that your angle, it is minus 180. The asymptote of this is minus 180. If you look at the quadrants for this, yeah, let's think in terms of quadrants here. So when omega is small, right, then this is a plus. Your real part is on the is positive, and your imaginary, yeah, that's negative, right? So the real part is positive. So in terms of your position of your of your complex number, we said for small values of omega, your imaginary part is going to be negative, right? The denominator is all positive, so we don't have to worry about that. But the imaginary part is going to be negative, and then the real part is going to be positive, right? This term will be small. So imaginary part negative, real part positive. So so we are down here. So somewhere in this quadrant, right? Is that right? Real part is positive and imaginary part is negative. So we are starting out down here. So we start out doing this kind of thing. And then when omega goes off to infinity, then your imaginary part, this is going to be also minus infinity, it's going to. And then here, this becomes much bigger. So this goes to minus infinity. So minus, which is here, right? So it's also going to 180 degrees, but it's approaching it from here now. So that's what's happening. It's close to 0. The angle is close to 0 here, and your function is doing this, right? And so it's starting out. If you were to draw the angle here, the angle is looking like this. It's close to 0, but then it goes more negative. So if you look at the next point, it's going more negative, and it's swinging all the way around until it reaches here, right? So the angle is doing this. So it is actually correct. It does go to 0. It's just that we didn't account for the quadrant. So the quadrant tells us it's actually minus 180 degrees. So like we said earlier with the arctan, yeah, if you only look at the ratio, then you get the wrong impression. You have to keep track, because here we were just looking at the ratio. Whereas if you separate the quadrants, which is what we did when we started to look at the two components, then you figure out that, well, yes, it is the arctan of 0, but it's in a different quadrant. So because the quadrant is different, then it's minus 180 rather than the 0. And that is what we are seeing here when we plot it using the code. It was 0, and then it goes to minus 180. If you didn't have two terms in the denominator, if you had just the one term, then you'll find that it goes to infinity. In fact, I'm very tempted to actually do that here. Do you follow the explanation for that there?
Yes, Prof. Just when you get plotting the Bode plot for your process, you rationalize and you obtain that final form, which is in the square root. Could you have just started from the beginning without rationalizing? So just substitute SIW and then put it into 20 log.
Let's see. I think that is something that I do, but you see, what we need to express eventually is this form. We need to put it in a form like this. We need to say this equals magnitude times e to the argument, right, of this G. So this is the form that we seek. So you do need the magnitude here. So to evaluate the magnitude, yeah, you can't really do that with the denominators like this. Yeah.
Then how come we are doing that for the controller in the nodes?
Let's have a look in the notes. Is it this?
Yeah, this one.
Okay, so if you look here, what I was saying was that in your denominator here, it's not really necessary to go and multiply. There are different ways to rationalize it. So here, it's very clear that the magnitude is going to be tau I omega, right? Because it's a pure imaginary number. We don't have to go and, you need to square root and all that if it's, a complex, if you have a real part and an imaginary part, then you need to, to use your Pythagoras to get that. But if you are sitting here and this value is 2, then clearly your magnitude is a 2. If here the value is -3, then clearly the magnitude is 3. So in the same way, in this denominator, if it's a pure imaginary number, then clearly the magnitude is just tau omega. So that's why we didn't have to do that here, really.
Okay, thank you, Prof.
But what I don't like is I've kind of left this part hanging, this middle term. I would like to just work a bit more on this and release a solution where this part is taken better care of. So I'll, for the rest of it, it's fine. All this, so that angle part we've resolved. You can see how to plot these other parts, right? Using that your crossover point. Just this part, is a little bit unresolved. So I'll release a more detailed solution with this part taken care of as well. Okay. So this now is all just about the process, right? So this tells us how to draw our Bode diagram for the process itself. And so you get your L and theta. Let's just clear that. So that shows us how we can go about plotting L and theta. Oops. So you can produce a Bode diagram. So definitely for the test, you must be able to draw a Bode diagram. And then, and it might be by the time we add up the different terms, the line slopes, and then it unslopes, and it might even do that. And then this one typically goes through a couple of changes, might even do that. Could go up again, depending on what the other terms are, if you have lead terms. And always use the convention, stay under 0. So you'll have these two. And then your next step, of course, is to go ahead and choose sections through this. So choose different values of omega. And then you would go and plot that on your Nichols chart. So let's get a bit of a snapshot of a Nichols chart. Okay, let's draw a nice Nichols chart. Let's put this back. Okay, just snip that out. So there's our Nichols chart. So you would go and choose all these points. So this point, you read up this L value and this theta value, then you look it up here. Maybe that defines a point here. And then you look up this value and this theta value. So in this case, L didn't change, but theta went down. So you keep the L and your theta goes down. So you might be here. And then maybe this point and this point. So L has gone down and theta has gone down. So it's there. So you produce all those points and then you draw this curve out. And then you look at what adjustments must you make to get yourself tangent to this line here, this line which gives us nice performance. Yeah, that's basically it. Any other questions or comments there?
Sure. So the first question you did today,
The gain margin and phase margin.
yeah, if we say that just by looking at the Nyquist plot, we'll need to move like 0.5 on the real axis. Is that can we measure that on the the Bode plots, that magnitude of 0.5?
I'm not sure I get the question. Are you saying if you see a 0.5 on your Nyquist?
Yeah. So to say where we need to go to be -1 and 0 is, let's say, uh, a distance of like -1.5.
So this distance is -1.5. So let's see. So if your function crosses here, if your point was here, -1, and you are saying if it's crossing here at what was it? What value did you say?
minus 0.5.
0.5, right? So so the width here is 0.5. Yeah, then your gain margin is 1 over that. So gain margin is defined as 1 over that distance, 1 over 0.5. So that's going to be a 2, right? Was that what you were asking?
Yeah. Now can we, by looking just at that gain margin, can we say how much the Bode plots have to move?
Well, it depends. Are you asking how much it has to move for it to be unstable?
Yes, unstable.
Okay. So this is gain margin, right? This is not L itself. So L is the log modulus of the magnitude. So 20 log 10 of the magnitude of G. So what you can do is on your Bode diagram, you can draw that critical, this value. So we know that this is a 0, right? So on your Bode diagram, you've got L against log theta, log omega, and you can draw the 0 line there. That's the 0 line. And now when you plot this, this magnitude, right? And obviously you can recalculate the magnitude every time as we were showing. Now, clearly all these magnitudes are less than 1. So the log 10 of that is going to be less than 0. So when you plot all these magnitudes, you are going to see something like that, right? And yeah, you'll get to a point here. So you are asking a bit about this, right? So that's going to be some point here. And the way to detect that is, as we said earlier, using the angle graph as well. Just moving this. So here, you've got your angle. So the way to find that the gain margin is through the angle. You have to think about, right, from the L graph itself, you can't say where this point is going to be. The only criterion for crossing here is the angle, which is 180 degrees, right? Or minus 180 degrees. Because there's nothing special about this value in terms of magnitude, right? With magnitude, okay, you've specified 0.5. So if you knew to look for 0.5, then you could do that here. You could just say, okay, where's 0.5 and where's 0.5, then it's there. But you didn't know, if you are trying to determine this value, then you don't know this number. The only thing you do know is that it's crossing at the minus 180 degree line. So then you would have to go to the angle part and then look for minus 180. So if minus 180 is here, then you say, okay, so that's the value of theta that I'm looking for. And then you say, what's the frequency when that happens? So that's my log omega value. So now we know the omega value, then you can just produce that up and say, okay, there's the omega value where the angle is minus 180. Then I can look up here and I say, okay, so that must be where it's crossing. And then you can say that's the L value where we are crossing the line. Is that what you were asking about there?
Oh, okay, yes, Prof, yes. So we don't use the 0 and then move to the theta. We do it the other way with the 180 degrees and then move to L.
So when we are trying to get the gain margin, that's what we do, right? When you are trying to figure out in terms of magnitude how far away, then yeah, you start with the angle and then you can kind of backwards work it out. But there's also the concept of phase margin, right? So we worked out in terms of magnitude how far away we are, but we also need to know in terms of angle. So when it comes to angle, then we look at the crossing over on the 0. And here, in fact, you would say, actually, we never ever get to the unit circle, right? So in terms of angle, the way we work that out is through, remember, to figure out the angle, you look at when the function exceeds that magnitude of 1. And then that's the angle there, right? But in the case where it never exceeds the 1, right? If this curve just stays on the inside always, then we regard that as a kind of infinite distance away, that there's no, if we know it stays inside 1, then that means it's never going to be unstable. And so in terms of angle, there's no concern. The only other thing, well, in fact, there's no concern at all. Then we know we are not close. So yeah, in terms of the phase margin, then you have to worry about the magnitude being 1. So that's when you have to worry about crossing over the 0. So it's like you have to use the opposite one. In terms of angle, you use the magnitude. So that's where you look for L being 0. In terms of the gain margin, you start with the angle and then you try to work out L. Is
Okay,
that what you're asking?
thank you very much, Prof.
Sure. Okay, any other questions or things you want to cover?
The date of the second test, is it on the 18th or the 21st?
That's the 18th. So yeah, I think that's the same as the tutorial period. Yeah, the 18th is the date of the test.
Prof, we have a Zulu test on the 18th.
Oh yeah, I think this had been sent. I can't remember now. I think the class rep had mentioned that, and then we moved it to the morning or something like that. I must just check that. I can't remember on the emails. It's probably on the announcements. If yeah, I'll just check that. So it's fine. I think we said 10 o'clock in the morning or something like that.
Okay.
Okay. All right. Anyone else? Any questions? Anything you want me to cover? Okay. So if there are no further questions or comments there, then that's it for this revision. And then, yeah, this field, I must say, it's it's really fun in terms of the maths, but there are more contemporary ways of doing control now. So neural networks, I really regret that we haven't gotten that into the course as yet. But yeah, neural networks, that should be a thing that's in the course. So in my research group, we cover machine learning topics in some depth. So that is a way you can access it locally. But of course, there are lots of resources out there for neural networks and so on. I must say also, there's a great deal more interest from companies in machine learning, and neural networks are one, but there are lots of other great algorithms in machine learning. So yeah, I hope you are all taking the time to study beyond what we've done in ChemEng. It's fine if you're staying comfortably in ChemEng. Well, even there, even in ChemEng, machine learning is penetrating quite far. So in addition to the material we cover here, which you'll find actually goes quite a lot into some of the machine learning concepts, you should keep studying and keep growing your knowledge in this field of algorithmic model development and so on. So you can follow on the YouTube channel. You'll see every now and then we release a few more videos about machine learning, and from the research group you can attend the seminars and so on. So this is all talking about beyond this semester. Yeah, I don't know if you were hoping that the studies would come to an end. You'll find study never really comes to an end. And hopefully you are enjoying that fact, and that you keep progressing with all that. So basically that's it from me for the course. Yeah, and of course, you can email me with any further questions and so on. The past couple of weeks have been extremely busy, but things are much better this week. So please do go ahead and keep sending me your questions if you have any further things to cover. Okay, thanks very much, everyone. So on the chat, yes, we can post this recording up. So yeah, someone there says that I thought the test was moved to the 21st. So I'll check on the announcements. I'm not too sure. Yeah, I'll just confirm that one by announcement also. All right. Thank you. Goodbye, everyone.